Bom dia, good morning. So today I want to, since we're getting close to the end of the course and doing things, right, with some research things, I want to show you something which when I saw this for the first time, I thought it was very interesting. And it's a different way to compute derivatives on the computer. So it's this paper by Squire and Trapp. So we'll talk on numerical differentiation, and I'm going to talk about a paper which is by Squire and Trapp, and the title is Using Complex Variables to Estimate Derivatives of Real value functions. So this is SIAM review. 1998. There's some time ago, and it's a method. I mean, I found this very interesting, and it's not well known. So it's good to see how complex variables comes in a way, again, to help us to compute derivatives. So here's the paper. Let me see, page it. It's not working very well. Okay, so we see two things up there which I will repeat here, and we're going to compare. So the first thing we see up there, so how complex variables is going to come in to compute derivatives? Something very simple. Okay, so now it's not even PDEs, but of course I would like to use some of these ideas in PDEs. So we can use, say, central difference. Central excuse me, finite difference. Excuse me. And I'm going to say that the derivative f prime of x0, isn't it x0? Excuse me. This is central difference, sorry. So this is second order, and this is very simple, right? So let's put it here. So this is order. Excuse me. I don't know why my starts itching. Okay, and now here is something that looks, when the first time I saw this, I thought, this is weird, but it's interesting. So another way now to compute is the complex scheme. Let me just call it like this. And f of x prime, f prime of x0, sorry, is computed as the imaginary part of f x0 plus I h. So it's a complex imaginary step. Doesn't this look weird? It looks weird at first, right? But we're going to make this clear. Divided by h. Okay? So, very strange. And what these authors, okay, what this is also going to be order h squared. We're going to show. I'll show this to you. And what the authors say, and actually they show, is that, I'm going to call this maybe formula star 1, formula star 2, is that star 1 as h goes to 0, star 1 has a cancellation problem, and star 2 does not. Okay? So this is a very short paper in SIAM review. I think it's actually in the section which is called classroom notes, something like this, because it's more, the math is very simple. But you look at this, doesn't it look strange? Right? Do you agree? I mean, I'm going to compute numerically the derivative of f, a real valued function, at a point x0, by doing this funny looking formula. This is basically calculus, right? So if this would be calculus, it would be a little bit like the secant method, right? You can have a tangent here, a tangent there, or the secant method. This we know, Taylor series, blah, blah, blah. Now, this formula, super strange, and it's advertised that it is good. It is good, of course. I'm going to show you a table in just a while. But what's going on here? What's going on here is this. You have a real valued function, f of x, but you complexify it. Okay? So you complexify the function. You take the imaginary part to divide. So here, the cancellation problem, this is one thing that I mentioned to you before, right? That we cannot take, say, the limit on the computer, right? As we take in mathematics. As h goes to 0, this guy approaches this guy, and this goes to 0, and we know through calculus that that's the definition, one of the ways of writing the derivative, okay? But if you do it on the computer, if you want, you can try. This is not a homework, but you can try, you can play with it, is that this is going to give us a 0 divided by 0, and it's going to go bad in some way. I'm going to show you the table, square and trap. Do this, and at the end, you just get a cancellation. This comes out 0, right? It could blow up, but it just comes out 0. Now, this one doesn't. And let's understand why, okay? Okay, so first thing, this is f is then, so let's play this, complexify f of x. It's a real valued function, but look, say, if it's, one example I might show you later on, it's like, if it's sine of x, you're going to make it sine of z, of x plus iy. That's complexifying the function, okay? So let me just write it here. F of x0 plus ih. So this is all the math, it's Taylor series that they have in their paper. Simple but smart. And look what happens. Take Taylor series. Let me write this like this. Nothing dramatic, right? Now, if I take the imaginary part of this, I don't care about this guy. Correct? Because the imaginary part is this guy has an eye. This guy has an eye. I don't see this guy. I don't see that guy if I just take the imaginary part. And then that's the formula that's over here, right? You take this, equals this divided by this, it's order h squared. Agree? Right? So you got to be careful. One thing they say in the paper, and depending on the software you're using, you got to be careful. I already mentioned this to you, that sometimes complexifying things in the computer, you got to keep track of things. Sometimes if you have branch points or whatever, and you got to take, there's the prices to be paid. This is when you have to have good code taking care of complex numbers. But let's look at this from here, just the pure mathematical point of view, okay? Now, this guy here is good from this formula because you don't have the cancellation problem. And basically, that's all the math they somehow show in the paper, right? And then they put it in the computer, do some smart calculations, and I'll show you, I'm going to project the table that they show comparing this with this as h becomes smaller and smaller, right? And they use double precision, 18 digits, and they go with h very, 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 very small. They kind of do the limit, and they have a lot of digits of accuracy comparing with the exact value of a derivative, okay? Now, this puzzled me, and they don't have this in the paper. Of course, they kind of know this, but they don't have anything in the paper. So I want to see, what's going on here? So look what's going on. I'm going to do one more simple calculation of complex variables, and it's nice because then our intuition comes back, starts working. My intuition up to here doesn't work very well. What's going on? You see the calculation, see the algebra, okay, right? But what's going on here in a more interesting way? So look at this. So calculation not shown in the paper is this one. So f of z is a complex valued function. Well, it's our function, our real valued function, complexified. And I'm going to use the following notation. Real part is little f. Imaginary part is little g. Okay? So of course, because this is a real valued function, f of x is this, right? Which is this, but this is 0, right? Because this is a real valued function, right? Remember. Real valued. Do you agree? If this is real valued, that means, right, I'm saying like this. X, y, I'm in the upper half plane. This is y here is bad. And the trace of the function here, f of x, is f of x 0. Since it's real valued, there's no imaginary part. G is 0. Okay? Which means that the boundary why am I holding two chalks? I don't know, maybe. So, so it means that the trace of this function, let me put it this way. These are two harmonic functions, right? And the boundary value, the trace of this guy is 0. Okay, could be. And this one is our function we started with. Agree? Am I explaining clearly? Okay. Now, so this is, let me write like this. This is real valued trace of f, right? Because that's the hypothesis we started with. The trace means the value on the boundary. In this case, the boundary is the real axis if you think of the upper half plane. Now look at this. Now if I write this, imaginary this is our formula. This, look, note that this, okay, is the same thing as this. Why? because, well, this is the same, and the imaginary part of this is 0. We just confirmed this. Agree? But what is this? And that's the cool, I think they should have put this in the paper. Particularly, it's supposed to be a more elementary paper, right, to help students. This is nothing more than this. Look, it's the imaginary part of a derivative on the real axis with a complex step, okay? Right, I could put the I there. Maybe I should have put the I there, right, to be more precise. But this gives me the derivative of the harmonic conjugate. So let me see, maybe I should have put the I there. Let's see, if I do this, maybe this in the notes. Yeah, maybe the proper thing would be, I think, double check. I should have the I here, right? Because it's a complex step on the vertical axis. Okay, and this from Cauchy-Riemann is this. So the thing I found very interesting, very cool, is that this formula, which we see in the paper, which looks like a bizarre formula, right? The paper says, well, this formula comes from the Taylor series expansion, okay? And it seems like a good formula, right? Because it has no cancellation, right? In this sense here, 0 over 0. And then they're going to compute this and show this. But then I wanted to get some intuition, and the intuition is that basically what this formula is doing, it's computing the y derivative of the harmonic conjugate of f, which is basically the x, what we want. Okay? Without ever, really having to think this way. So let me go to the computer here and show you the table they show for their computations. Okay, this is just the things we did. Here's the table. So the function, let me write on the board because the projection we can't see it so well. So the function they are doing is this function here, and the point, I forget what it is. Well, I think it's x equal to 1.5. Well, it doesn't matter, okay? So this function, which has a few derivatives, right? Because the square root, and look there, they're computing with say double precision, and the first column, equation 1, so column 1, let me put it like this. So what they're doing, because in the video we can't, in the project, this is finite difference, and this is the complex method. Okay? So with the finite difference, as the step size starts getting smaller and smaller and smaller, when it gets down to already 10 to the minus 14 or 15, the solution is going bad, right? And then you see nothing. It becomes 0. So that's wrong. Okay? So later on, if you remind me, I can send you this paper in particular because here is not very good to read, okay? It's a few pages, simple paper. And then on the right-hand side is the complex method. And as you can see, I don't know if I can make it bigger, maybe not. You can see from 10 to the minus 8, when h was over there, d 10 to the minus h, it basically has all the digits of accuracy and it doesn't change anymore. So it's very accurate, right, for very, very, very small h. Okay, so this computation ends up being very accurate. And I found this very interesting. And then in a recent work, it's not so recent, I mean, it has 3 years, but now it's a little bit on hold because I'm waiting to have time to do applications with it. I'm going to show you something that I did in terms of research using Hilbert transforms, spectral accuracy, things you got your hands on, which I also find very interesting. I think you notice my enthusiasm when I talk about this. And I'm going to compare with this. So with Hilbert transforms, I sort of discovered this sort of method to compute derivatives using singular integrals. So you compute, you can't say this when you're studying calculus, right? Because I'm using integral to compute a derivative. So if you tell a calculus student that, it's not very instructive. But it has spectral accuracy. It's interesting mathematically. It also has some complex variables. I'll talk about this to you. But one problem it has up to now, it's like mathematically interesting, but it's not efficient. It's expensive. So I have ideas to make it a little more competitive and also then apply it to PDEs. So this is one thing I'm still kind of thinking about. So I'm going to now share with you this other sort of preprint of mine, which eventually I'll come back to this. I hope today I have time. If I don't, will be next class. Okay? So this is the idea. So first thing is that this I think it's interesting is on its own, because it's like it's at first a weird, different way to compute a derivative using complex variables, this and that, but it has advantages. And it's kind of interesting. And what I like very much is this, that actually to compute this, you compute the y derivative, that means in the other direction of the harmonic conjugate, without ever writing explicit all this. So it's kind of cool, okay? So let me go now and open another paper to show and discuss with you. Visualizar, que modo de leitura, né? Maximizar, eu sempre me enrolo aqui, né? Aqui? Obrigado, tá. Agora tem que fazer isso aqui maior. Ctrl Shift mais, né? Só botar ele de cabeça para cima, tá? Okay, obrigado. Okay, so it's good also that this forces me to mention a few things with you that we saw during the course, you saw during your work, some of your homework, and will lead to this problem. So now I'm going to show you how I'm going to do this. I'm not mentioning it yet, but I'm going to compute. I'm going to compute derivatives using singular integrals and quadrature. Well, you already know what kind of quadrature kind of integration I'm going to use. What is it? For singular integrals? Alternate trapezoidal rule, right? So, and the alternate trapezoidal rule, you know, the paper which is a reference is this paper by Sidi and Israeli, okay? So actually, let me give away maybe one thing, because I think I'll have time, but just make sure. One thing I'm going to use is this. So if this is the Hilbert transform, okay, so we saw the Hilbert transform of X with the cotangent, that is the periodic one. I'm not going to write here, later on it will appear. We also saw the Hilbert transform of the derivative, okay? And there is one thing I think I never mentioned to you, which is a known property of the Hilbert transform, is that is this property here. Okay, so basically, if I put the minus sign here, it's almost like getting an inversion, going and coming back, okay? So I'm going to use this formula, and I'm going to use the formula for the Hilbert transform of the derivative to compute derivatives. Because if I use the Hilbert transform of the derivative, and then I apply the Hilbert transform to it, I get back the derivative, okay? So you'll see this in a second. So let us review things we know about the alternate trapezoidal rule. So now I'm going to mention about the alternate trapezoidal rule. Okay, from the paper of Sidi Israeli. So I'm not going to show the proof of Sidi Israeli, but I'm going to mention ingredients that I mentioned very quickly. I'm still going to mention it a little faster here. I mean, I'm not going to get into details, but at this stage of the course, I'm going to give you information that will stay, I think, in your minds in a way that if you need to read the paper, at least that theorem, which is the one which is, there's many theorems, many things in their paper, but the one that's the most important for us, you will have the information, okay? So this is basically, let me read it for you since it's not very, it's very clear. Wellington, can you read it from the, você consegue ler? Okay, good. So can you read? Probably on the computer, for those in the video is better, right? So what the theorem says is this, okay? So the first theorem of Sidi Israeli reminds us a little bit of the Krasny way to integrate the singular integral. Remember, you worked on the Krasny and the other one, right? So look at this. They say, consider the singular integral I, Cauchy principal value of capital G of X, where L is the period. Okay, so it's a periodic integral where L is the period, and G has a pole at x equal to y, someplace in the middle of the interval, x equal to y. Okay, and let's suppose that then the integrand can be represented in that form, little g, which is the singular part, plus a regular part. Okay? The singular part is g divided by the pole, and the regular part is g tilde. You barely can see the tilde there, which is the regular part, but little g, both little g's are smooth. Okay? And the theorem says that both g tilde and g have 2m derivatives. So there are 2m times differentiable on the interval. Okay? That's the hypothesis of the theorem. Then the grid size is h, okay, and so on. And then they show that this quadrature here, okay, I'm missing maybe the last line of the theorem. Let me put it up here. Okay? So the last line of theme came in the other page, sorry. So they say that then this quadrature here, which look, it's like the Krasny one. It just skips one point. J different from K. Okay? So this quadrature skipping one point is first order. Okay, here it is. Yields the error E of n, which is first order, which is the value of the little g's, g and g tilde at the pole, right? These are the smooth parts, times h, which I put there in red, plus in order h to the 2m, which is the regularity to some extent, related to the regularity of the little g's. Okay, so if you skip just the point where you have the singularity, your integral is first order, just like what Krasny was doing. Okay? But then they realized the trick to kill. You see, if you can kill the first order term, which is first order in H, which is the red term, if you can kill that term, you immediately get spectral accuracy. Because then you get an error that depends on the smoothness of your function. Okay? Or the smoothness of the smooth part of your function, because you have the pole. So you basically eliminate the effect of the pole. You agree? You understand what I'm saying? Does it make sense? Okay, well, ask questions, okay? So again, if you can kill that first term that appears in red, which is order H, then you immediately get a very high order accuracy, which is like spectral accuracy because it depends on the regularity of the function. The first order term doesn't depend on the regularity of the little g's, right? So how do they do that? Well, they do that using a known trick in numerical analysis, which I'll show it to you. I'm not sure if you know, so I want to mention it. So to get the second theorem, which is this. This is the second theorem of the paper by Sidi and Israeli, okay? I mean, it's not the second theorem in their paper, but it's two, I mean, there's many theorems that are up, and then there's these two together, okay, the one that comes just after. And then they say the following. Look, take the hypothesis of theorem 1, okay, and let's call the quadrature that we saw above capital Q of n, with n points, okay? Now, if they perform a Richardson extrapolation, right, and they write now a new formula, a new formula here, which is K tilde. I don't know if you can see the tilde, right, but Q tilde n of G, and this is the Richardson extrapolation. I'll explain it to you what it is. Then, well, you have this formula here, which is basically the alternate trapezoidal rule, and the error becomes h to the 2n. You cancel that order h term. So, out of curiosity here, who knows what a Richardson extrapolation is? You heard about it? Yeah, but don't remember. Okay, good. Again, I always like when you don't know something, because more things to share and teach, okay? Look what is the Richardson extrapolation. It's not that difficult, but a very smart idea by Richardson, which is this. Well, here's the explanation I'm going to give you. Soon I'm going to put it on the board in a more generic form. That actually find it, I was checking where it was an easy place for you to find. You can find it in Wikipedia, okay? I'll write it on the board. But look what Richardson extrapolation is. It's a very nice trick. You use your same method twice. That's the price you pay. If you use your same method twice with two different grid sizes, you can kill higher order terms and make your method higher order. So here, what is done is, look, this is the integration formula we saw above, just like I'm calling it the Krasny type 1, where you just skip the pole. This is Qn. And this is the same method, but now with 2n, which means with an h over 2 size. Okay? And the new composite method, Richardson extrapolation, is that you're going to do a new method, qn tilde, which uses the previous methods like this. You're going to multiply by 2 the one with a smaller h, subtract this one, you get this formula here, and you get a higher order method. And that's the alternate trapezoidal rule. Okay? So to help you, I made myself a note from, say, Wikipedia. I was looking, where can you guys find an easy reference to Richardson extrapolation? So I'm going to write it on the board now. Okay, let me erase here so I can use this board. So what is Richardson extrapolation? Okay, so let me actually put here, because it's easy, people can refer. You can find this in Wikipedia, this explanation, okay? Very simple. So take a method. So this is what we want to approximate. And this is, say, let me call it our discrete approximation of step H. Okay? So like a Taylor series, okay? When approximate a derivative or whatever, this is the exact value the guy we want to approximate, and this is approximation, right? So you might try to get, with this method, you will get this guy, order Hn approximation. Okay, so think of it this way. Now, define a new function, and this is the Richardson approximation. So define this, I'm going to call it R. That's the notation is used, R of H t. So define a function of H. Okay, define a function of H and t. You will see what t is. And the function is like this. Okay, so basically then just think of, right, H and H over T as two different step sizes. So if T is 2, right, you have H and H over 2. Okay, so you take this function, okay, and now you substitute square 1 into square 2. Right? You have the same bracket here. minus 1. And this will be equal to so we gain an order, okay? So you can see, right, as you multiply this, there's going to be some cancellations here, blah, 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 right? And you get this. This is Richardson extrapolation, right? So you see the one that was done above was n was 1, t was 2, right? Because it was first order. N was 1, t was 2, and blah, blah, blah. And then that's the one we see over there for the Richardson extrapolation, okay? So you gain an order. That's a way that you can sort of improve a method, right? Some integration methods, some differentiation methods use this trick. And here, the alternate trapezoidal rule comes basically from the method that Krasny used. And the Richardson extrapolation, poof, gives you spectral accuracy and the super simple, super nice alternate trapezoidal rule that you tested on the computer, okay? And just one comment I forgot to say is that the proof of the first one, for example, the first theorem, the proof of the first theorem of C.D. Israeli, you know, to show its first order and so on, they manipulate the integrals and so on, and they sort of desingularize, put things together, blah, blah, to prove. And you remember what it means to desingularize, right? Remember, right? You just multiply a 0, which is written a singular way, and you desingularize, okay? Okay. Now, okay, so let me continue now with, right, my strategy. So using now the alternate trapezoidal rule, right? This was just for me was just an excuse for me to mention to you a little bit of C.D. Israeli's paper and the Richardson extrapolation, which you had never heard. It's something simple. It's in numerical analysis books here and there, so it's important for you to know. Okay, now let's go back then to the singular integration. Okay, so here's a graph for the alternate trapezoidal rule. And now I'm going to present what I call the distributional finite difference method. Okay, so here, maybe let me erase this part here so I stay close to the video. Okay, so what I'm going to do now, let me repeat over here. I have this Hilbert transform here, which is the periodic one. Okay. And we also have the other one, which is, I might get the constants wrong, but I'll fix it afterwards. This one, I'll check it afterwards. No, I actually check it now, sorry. Yeah, I just got the 4 pi there, okay. So what I'm going to do now, I'm going to use this formula here. Okay? So I wanted to check, I was very curious, this was something that was in my mind for many years, and I still have to follow up on this. But the first part works is that I said, look, you know, using this formula, I'm not quite using a finite difference method, right? I'm not using a spectral method in the sense of using Fourier or using some basis of functions. I'm not doing anything. I'm just using a singular integral, okay? I know it's expensive, but I wanted to see what's going to come out of this. Right, I was very curious, and that's in this preprint. So I'm using the Hilbert transform twice, which is using the alternate trapezoid rule twice, which makes the method expensive. It's order n squared, right? Because I'm using 2 integrations and so on with n points. Okay? But I was curious to see what I could gain out of this, even though it's expensive. And right now it's not very efficient from the computational work, but it is efficient from the numerical error side, and that's what I want to show to you. Okay, so this, when I discretize this by the alternate trapezoidal rule, and I reorder things, okay, I reorder things. So let me actually also put my notation here. So d squared of f is this. Is f j plus 1. Let's see which way I'm using. Yeah, let me put it minus 2fj plus 2fj minus 1 h squared. But, okay. Let me just go up one thing, make sure my definition is right, because that appeared above. Yeah, so let me write this definition this way, which is better. So this is the center difference in this way, and this other one is d2 jl of f is going to be okay, yeah. Okay. So, yes, Christian? Aqui? No, this is plus 1. This is plus 1. This is plus L. And this is minus L. No, where? Onde? Aqui?
É no de cima, na diferença central. É menos 2FJ mais FJ menos 1.
Ah. Yeah, thank you. Yeah, sure, sorry. Thank you very much, yes. Okay, thank you. So what is this? This, okay, so look what happens. This is basically the molecule for this guy is this. And the molecule for this guy is this, if L is equal to 2. Right? You're skipping points, right? So here, like this, the dark nodes are the ones we are using, okay? So one thing was very, very interesting that when I used, so what is this formula saying? I have to explain to you. That's why I had to draw this. That all I'm doing is using this plus alternate trapezoidal rule. So I'm using this identity, right, plus alternate trapezoidal rule. Okay? That you know how to do. You could program that because you already did the alternate trapezoidal rule for the Hilbert transform. Okay? When I do this, and it took me, and I start seeing some symmetries, you know, in using trigonometric relations, because you know, cotangent over here is minus cotangent over there, blah, blah, and I do this, I can reorganize things and rewrite this formula in the way you see over there. So there's a double sum. The fact that D is odd and this other one here, L, is odd, is because of the alternate trapezoidal rule. And then I reorganize the guys. So look, this C here is the cotangent. This S here is the sine. Okay, exactly. Pum and pum. Okay, you see? And then these differences that appeared here, I was able to reorganize them, and that kind of amazed me. When I reorganized these differences, look, there's a bit of, in the trapezoid, in the Hilbert transform of the derivative, there's already a difference here. It looks like a continuum of differences, right? But since we're using spectral accuracy and the alternate trapezoidal rule, when I reorganize these guys, ooh, sorry. I have to make this bigger, sorry. Ai, ai. Como é que agora eu... Control? Obrigado. Obrigado. So when I then reorganize things, to my surprise, I was able to write this as a formula with these integrals which are summing over second derivatives of the function. So I'm kind of integrating over second derivatives, centered second derivatives of the function over a bunch of scales of my grid. What do I mean by a bunch of scales? 1 step, 2 steps. It's actually, to tell you the truth, you will see it's just odd ones. It's going to be 1 step, 3 steps, 5 steps, and so on. I think I have a picture in a little while. So basically, the alternate trapezoidal rule, to compute the derivative, I'm actually integrating a second derivative to get the first derivative. Okay? I think I have a graph. Here it is. So what this identity with the alternate trapezoidal rule told me at the end is that I have second derivatives, numerical, the computation of second derivatives, that I'm going to sum them up. That means I'm going to integrate, and I'm going to use all second derivatives from these scales. Look, for example, let's look here. If my singularity is on this node, right, I'm going to compute this second derivative, then the one on this scale, then the one on that scale, to the maximum I can on this grid. Okay? So I do this on this side, and I do that on that side. Remember, I had like 2 second derivatives that I was computing. And at the end, this is expensive. I yet don't know, you'll see at the end, I yet don't know how to make this. I have some ideas of making this a little cheaper, but then I lose a little bit of the spectral accuracy, but not in a dramatic way, right? It's just a technicality, I think. I have to verify. But this formula is very accurate. It's not very efficient in terms of computational effort. It's expensive, but it's accurate. Okay? So this is what the formula is doing at the end. Okay, here I'm comparing it with the, you already saw this, the square and trap. I also looked at the differentiation matrix. Whoops. So this differentiation matrix here is for the finite difference. So I can compute derivatives numerically by making a matrix multiplication. Do you agree? Right? I mean, if I have, right? If I have one of these methods, I can do m times f. This is going to give me the vector, an approximation of f prime, right? So, and each line has this. Look, 1 minus 2, 1 divided by h. So here it is, divided by h, right? And this is for the center difference. I'm sorry, it's not for this one. I'm sorry, it's for this one, of course, right? 1 minus 1 to h. And then these are the differentiation matrices. So let's look at the differentiation matrix for these other methods. So I asked you, right, as one of your homeworks, to study chapters which talk about sinc functions, right? And there's the periodic sinc function, as you saw, right, in the study. So here it is, the Whittaker. So if you do using sinc functions, you probably saw this in Trefethen's book, which is the differentiation matrix using sinc functions, is this guy, where these C here's are these cotangents. Okay, you can recognize this, right? So that's why I told you also to do this homework. So we could also put all this together now at the end of the course. So this is the differentiation matrix. So my Hilbert transform method is spectrally accurate. Why? Because I'm using alternate trapezoidal rule. It is not Fourier-based. That means I'm not using Fourier methods to do it or any other basis functions. So the differentiation matrix is going to appear in a slightly different way because it's using another strategy. But of course, to leading order, it must be doing the same. And it's more complicated. Well, I don't write it. Yeah, I don't. This is the FFT one. Yeah, and I don't write it. Yeah, here are some of the terms. Yeah, I don't write it. I don't write it as a matrix. Okay? Okay, then I started testing this method. So I started testing this method, and I said, okay, since I have spectral accuracy, right, it should be basically as good as an FFT, right, because it's spectral accurate. So here is a graph for a derivative of sine of 5x, should be written somewhere. I think it's sine of 5x, yes. And it's one is on top of the other. Here I have three methods. I have finite difference, Fourier, and my Hilbert transform method. Okay? And actually, for this case, even the finite difference method is doing okay. Let me see if I have it. Yeah, oh, here it is, cosine of 5x. Just 32 points. The dots are my Hilbert transform that I'm calling distributional finite difference. Why distributional? Because I have the singular integral. I have a function that's not a function, right? It's a distribution, the kernel. And two lines are superimposed, which is the finite difference and the exact derivative. Okay, here I don't have, in the solid line with small decrement is the finite difference method. Okay. Now, in the bottom graph, I'm showing you the error. Okay, the bottom. The round-off error difference between the finite difference method and the FFT. So the my method, the Hilbert transform, is the solid line, and the dots is the FFT. So it's pretty good, and it's like 10 to the minus 6 or whatever, or 8. I can't quite see it. So it's a very good error, and the error is comparable. Both have spectral accuracy. Okay? But the structure of the error, as you will see, is a bit different. And that's what I want to show you next in the few minutes of the class. Okay? So here, I'm just saying, okay, all is good. Let's see if I can page here. Okay, here is a higher order cosine. So it's cosine of 30x, right? A faster cosine. And you see a little bit of a modulation on the curve. And the solid line, yeah, it's finite difference method. And the other one is FFTs. Let's see, where's top graph? Dots line and where's bottom graph here? Bottom. The round-off error difference between the exact and the method, solid line, and FFT is dots. Okay? So here it looks like, FFT is a little better than this other method, than the Hilbert transform. But then I did this case here, which I found it also very interesting. Let me share this with you. This is just, look at this. This is just cosine of x. Okay, cosine of x. But now I'm going to use lots of points, 4,096 points. Okay, so when I do this, I'm imagining that I'm in a problem where I'm not doing this because I have to approximate the cosine of x well. It's because I need information of many points, okay, for some reason. So if I have information of many points, suppose that, for example, I have a wave that is cosine, but that I have a variable bottom and I need to resolve the microscale, okay? So for the wave, I don't need all these points, but for the microscale, the coefficients, I might need all these points, okay? Or another thing too, I have a very long domain where I'm going to put a pulse, for example, a Gaussian, and I need, because the domain is very long, I need to put a bunch of points, okay? But now I just think about the cosine. Look what happens. If I need a lot of points and I want to compute the derivative of this cosine, okay, the solution looks okay, more or less okay, okay? But look at the error. The error of the FFT is a little bit higher than the error of the Hilbert transform method. The other interesting thing too is the error of the Hilbert transform method. It sort of, in some points it's a little bit bigger, in other points it's not so bigger, which means, look at these points where the error is smaller, it's the points where the derivative is flat, is 0, right? Now, why is the derivative? Now let me ask for your help. Why do you think that the derivative of the FFT sort of grew and became bigger? And that has to do with the fact, here's a hint, that has to do with the fact that I'm using a lot of points. Why is a lot of points now playing a little bit against me? Think of it in terms of Fourier. Right? It's just cosine of x, right? So instead of thinking of cosine of x, just think of e to the ix. Okay? That's the function I'm trying to differentiate. Okay? But what might be going wrong, it's simple, again, it's those questions which is simple, but if you've never been asked it, you start, your mind starts wondering, and let me help you. When I do a derivative using a Fourier method, okay, what do I do? Very good. You multiply by IK, okay? Very good. Now, if I'm differentiating just e to the IK, so you want to say something, Chris?
E aí, tipo assim, se eu estou usando um N muito grande, o programa fica rígido. Tem coisas de ordem diferente.
More or less. Very good. No, very good. Because what Christian said, so that people can get the microphone, is that if you have N very large, you're going on the right track. Maybe just, I'm not sure if I would say it's stiff, but you got the feeling. You got the right feeling. If N is very large, okay, you got the right feeling. I am to differentiate just cosine, let me put this here. I need to differentiate, so look at the intuition, but that's very good. If I need to differentiate the cosine of x, that means the only k that I really need is what? K equal to 1. Here's my finger, okay? But my hand here is pointing at the end of the spectrum, right? And you're correct. So if I put more and more n's, more and more points, I just need to differentiate this guy, but I have numerically this whole spectrum, and here it's populated by what? By round of error. Because I cannot compute cosine of n, just think of it as a signal. If you're working whatever you use your background, computer graphics, right? It's just a signal, right? Cosine. So I only have actually one mode, but all the other modes here, just like, right, are populated by round of error. When I multiply by IK, and k is large, right, this guy here is going to get amplified by 10 to the 3, because it's 4,000. It's k 4,000, right? Or actually k over 2, so it's 2,000, right? Because of Nyquist frequency. So this guy is going to be multiplied by 1,000. Where this guy, these order 1 guys, which are the relevant guys, are not. So it's not, I'm not sure it's quite the stiffness, but it reminds stiffness. So that's correct, okay? And look what happens. And look what happens. That's why the error sort of contaminates everybody. And if I do a zoom, I think this is the next picture. Look, if I do a zoom, right? Look at the difference here on the y-axis. This is a very small difference, right? If I do a zoom at the curve, you see that the FFT one, which is this black one, is getting noisy because I'm amplifying the high frequencies of the spectrum, which is just round of error, right? So it's not terribly bad. It didn't quite go unstable, but this might have some connection with stiffness. Stiffness, if I'm doing this periodically, this will grow, right? I haven't done this, but it's okay, right? It's not quite stiffness, I won't say, but it has relationships, okay? So you see this, this error coming in, and with the Hilbert method, Hilbert transform method, that does not happen. Okay? Let me show another figure. I'll come back to this maybe next class, I think. I don't want to rush over this. Yeah, let me show. Now look, this is one point I like a lot, and I want to explore with PDEs, and I haven't done this yet. First, because the method is expensive. I have ideas which came from the Squire and Trap thing to make the method maybe faster. I'm not sure. But this has to be tested with waves. It has not yet been tested with waves. But look, this is a starting point. If I have a Gaussian, okay, this is the exact derivative of a Gaussian, okay? And in this case here, I used 512 points. I didn't need much points. And let's see, the middle curve coincides, the exact derivative, the Hilbert transform, and the FFT method. All are very good, okay? But there's one thing that calls my attention here in this picture. which I want to explore in the future, and I haven't fully explored it. I haven't really explored it yet. I know it's going to probably work, but I have to make it, if I don't make this method a little faster, a little more efficient, I'm not so sure. It's interesting from a mathematical point of view, but it's not really an effective tool because it's expensive, right? But do you see one thing that called my attention? What, in the bottom graph of the error, let's see if you share with me my opinion that there's something interesting there. What do you think is interesting, Márcio?
The method is, o método ele é preciso, onde a derivada é aproximadamente zero, ao contrário do método de FFT, que ele tem erro meio que uniforme no intervalo todo.
Yes, so your answer is correct. I would just maybe say it in a slightly different way, right? You said, well, the method is very precise where the value of the function is 0, or the derivative is 0, and where you see the FFT one, which is the red dots, there's error everywhere, right? That's the point. The error of the FFT is small, it's very good, it's backtracked, but it's uniform. Why it's uniform? Because it's a non-local method, right? You go to all frequencies, and every frequency is like a sine or a cosine over the whole interval, and you're making errors over the whole interval, okay, even though it's good. This method, instead of saying the way you said it, which it's 0 where the derivative is 0, I would rather say, it's correct what you said, but I would say it in the following way. The method only generates an error over the quote-unquote support of the solution. So if you have a wave, right, the wave is basically 0 outside an interval. So not only the derivative is 0, as you said, but the solution value is 0, because a Gaussian, numerically speaking, is effectively, quote-unquote, a function of compact support. A Gaussian is not compact support because it decays exponentially. But numerically, it's almost like it is compact support. And you can see that there, the error is effectively compact support. It's only beneath the wave. So if I have, that's one thing I haven't explored, but I'm sure there might be interesting things there, that as the wave is traveling, it's only going to accumulate errors over where it was, whereas the FFT is going to accumulate error over the whole domain, right? So this is kind of very interesting structure of the error, and that has to do with the fact that the FFT is a spectral method which works in your transformed space, which is in the Fourier space, which the elements of that space, the modes, are non-local, right? This method, the Hilbert transform method, now it's expensive. FFT is cheap, it's n log n, right? It's much faster. So that's very cool and very good. But this method, it is, you don't have to, basically you end up not going to the transformed space, right? You stay in the physical domain, doing the second derivatives and integrating the second derivatives in a complicated way, and therefore the error is localized in space because it's only generated in physical space. That's a nice thing, but to be explored and to be explored in an interesting way, the method has to be made a little faster. One idea of making the method faster, I'm going to stop soon and leave this for next class, because then I'll go back to Squire and Trap paper, and what I'm going to do is first compare this method to the Squire and Trap. And this method is better than Squire and Trap, but it is expensive. So you will see what I'm trying to, I want to get to. Let me see if I have any other pictures here for today. If not, I'll stop here. In the next class, I'll compare this. I think then it's going to be graphs related to Squire and Trap. Yeah, we have like just 5 minutes, whatever. So next class on Thursday, I'm going to then compare Squire and Trap, this complex derivatives, okay? The one that uses not complex derivatives, better to say complex time step or complex stepping. It doesn't have to be time step, right? With this one, and and mention other things.